This lecture is titled Atoms, Molecules, and Ions, Oh My, and it is the introduction to AP chemistry. So if you look at this, there's a famous quote by Richard Feynman that says, "If in some cataclysm all scientific knowledge were destroyed and only one sentence passed on to the next generation, what statement would contain the most information in the fewest words?" This is a famous thought experiment that was done and presented to several different scientists. And Richard Feynman's quote was, "I believe it is the atomic hypothesis that all things are made of atoms." In that one sentence, you will see there's an enormous amount of information about the world if just a little imagination and thinking are applied. So, we are going to review our understanding of the atomic models, and we're going to focus on the empirical evidence. One of the biggest differences between a pre-AP and an AP chemistry course is the reliance on, or the understanding that you are going to understand the empirical evidence behind assumptions. So it's not going to be just the Bohr model of the atom, it's why is it the Bohr model of the atom. You need to be able to link the periodic table to the atomic model. You need to understand the general trends on the periodic table. You need to talk about ions and isotopes. You need to be able to calculate average atomic mass and percent abundance. And you need to be able to name different quantities. So these were all things that were covered in first year chemistry, but they were spread out throughout the course of the first semester. Those comprise the first chapter of AP chemistry. So let's take a look at it. First thing is, what do we know about the atoms? There's lots of things we know about the atoms. From a chronological standpoint, the first experiment that we have was Dalton's experiment. And what he did is he mixed various amounts of gases. These orange balloons are represented by hydrogen, and these blue balloons are mixed by oxygen. And what Dalton found was that whenever he mixed different ratios of gases together, he actually came up with a difference in products. This is called the law of multiple proportions that you have here. So if you were to look at it, he predicted that gases would combine to form new products. What he did when he did the experiment was he found that they always gave the same product. For example, when you mix two H's and an O, you get H2O, which we know is water. But when you mix two H's and two O's together, you would get an H2O and you would have a leftover oxygen. And likewise here, you wouldn't get H2O because there's not enough H's in order to make it work. So Dalton figured out from this that there must be small particles that are called atoms. And that's what he represented by a part, or a balloon full of an element, was an atom. That all atoms of an element are identical. So there is no difference between this hydrogen atom and this hydrogen atom. That you can't create or divide or destroy atoms. That you can't take an atom and break it in half. You can't take something from nothing and create an atom. And that atoms can combine in whole number ratios to form new substances. And that's what we saw with hydrogen and oxygen becoming H2O. And that's what we have: atoms can be combined, separated, or rearranged. So this was Dalton's theory, and it was good for a long while. But then Thomson did an experiment, and what he did is he said that, okay, I'm going to take these atoms and I'm going to make cathode rays, and I'm going to subjecting a gas to a large voltage. And then what he did is he took these cathode rays and he put them between charged plates. So he had a positive plate here, and he had a negative plate here. And what he saw is when he fired these cathode rays through, they didn't go straight through like you would expect of an atom that's neutral. Instead, what happened is they curled towards the positive plate. So what he knew at this point is he knew that this cathode ray moved towards a positive plate. Now, he already was aware of the fact that opposites attract. You should have learned that in physics, or you should have learned it in chemistry last year, but the opposites attract. And so because of that, he said that you can take an atom and you can divide it into smaller constituents. And he suggested that the cathode ray that he had was a negatively charged particle that he called actually a negative corpuscle of charge, but we now know as the electron. So Thomson was the first one to discover the electron based on the fact that you can deflect cathode rays towards a positive charge. Now, he also knew that the atoms are electrically neutral. If you take just hydrogen gas, it won't move one way or the other. So he knew there must be also a positive charge. And so what he did is he developed his model of the atom, which is referred to as the plum pudding or the chocolate chip cookie model. And it just basically says that everything is positive. Everything is positive everywhere in an atom except where these negative charges, or these little chips, are those negative charges that are spread out throughout the rest, which is positive. This is known as the plum pudding model or the Thomson model, and is based on the fact that you can take these these cathode rays and move them towards a positive plate. Next, you have Millikan's experiment. And what Millikan did is he actually measured the charge and the mass of an electron. So what he did is he said he used oil drops, and he had this really sophisticated apparatus in which he put oil that was charged, and he charged it using an electric current. He charged oil droplets and suspended them between two charged plates. So you have a negatively charged plate and you have a positively charged plate. So the electron is going, or the charged oil droplet is going to be repelled and then attracted. So it'll actually suspend itself in midair. Okay, gravity is going to be trying to pull it down, but this repulsion is going to put it up. And there's actually a little telescope where you can see where it is, and you can adjust the electric fields until it actually suspends exactly where you want it to be. Now, Millikan already knew Coulomb's law, and he knew that opposites attract. So by being able to manipulate the electric field until he suspended the oil droplet, he was able to figure out, okay, well, here's my mass of my oil droplet, here's the electric field required. Here's my mass of my oil droplet, here's the electric field that's required. And he was able to look and see a pattern in the data. Now, if you were to just look at this data, it doesn't appear that there's any clear pattern. But if you were to get into it and start dividing some numbers around, looking for things like the slope, you would see that there's actually a very clear pattern. Okay, no, this was not his real data, but it's okay because he allegedly faked his data anyway. A lot of people think of these historical scientists as being these perfect people that are wonderful experimentalists and those sorts of things, but in actuality, they had flaws and they ran into a lot of the same obstacles that we do today. And it is believed that Millikan faked his data in order to make it fit what he actually believed to be the answer. Okay, Millikan's analysis used Coulomb's law and weight. Okay, if you've taken physics, you should be familiar with something like this, where you have the electrostatic force is equal to the gravitational force. If you haven't taken physics, don't worry about that. This is actually not relevant to the chemistry part of it, but it's just trying to show you kind of how he did this. Okay, you might want to make note that he went ahead and set these two things equal to each other, and this actually allowed him to figure out what the charge of an electron was. Now, we generally recognize the charge of an electron to be 1.6 times 10 to the negative 19th now, which is a little bit different than what he found. But at the same time, he's measuring the charge of a single electron a long time ago. So you've got to give him credit for being able to do that. Next, we have the Geiger-Marsden experiment, which is also sometimes called the Rutherford experiment. What actually happened is Rutherford is actually the professor that's here. He was running a lab, and then Geiger and Marsden were students of his. Actually, Geiger was a postdoc. He was working in his lab, and Marsden was the student. And what they did is they set up this experiment in which they were firing alpha particles. An alpha particle is a helium nucleus. So what it consists of is it consists of 2 protons and 2 neutrons. And so what he did is he took these alpha particles and he fired them at gold foil. Now the gold foil, they were able to make just a few very thin because of the malleability of gold. So as a result of that, they had a layer of gold foil that was just a couple of atoms thick. And what they expected to happen was they expected all of these things to pass straight through. These alpha particles are very high energy particles. And so they likened it to firing a mortar or a rocket at tissue paper. But what they saw was, although a lot of the alpha particles went through and some of them deflected, every once in a while you would see a deflection in which the tissue paper, I say quote unquote tissue paper, the gold foil, actually repelled a mortar or a rocket, which is kind of hard to believe. So you can actually see that the analysis of this data actually led to the belief that there's a positive charge somewhere in the nucleus, and it's got to be a very concentrated charge. Now it also has to be very small. Now the reason why it has to be very small is most of the alpha particles got through. And what you see is, based on this close-up picture, unless an alpha particle comes into direct contact with this nucleus, it's going to go through. So the nucleus has to have the majority of the mass, it's got to be the positive charge, and it's got to be relatively small compared to the size of an atom as a whole. And that led to what we call the Rutherford model of the atom. A lot of times this is referred to as the planetary model, and what it says is that there's a positive charge in the nucleus, and that the electrons have to move around the nucleus at a variety of distances. So you'll have one that goes here, and another one that goes here, and another one goes here. And these electrons just kind of move about in circles just like the planets move about the sun. Then Bohr did his experiment. And in Bohr's experiment, what he did is he filled up these glass tubes with a gas, okay? And he did multiple different gases, so it doesn't really matter what they are. But what he did is he subjected them to a high voltage. Now, what you should know from first year chemistry is that if you subject an atom to a lot of energy, atoms will absorb that energy, and the electron goes up and the electron goes down, and it can produce light. Well, by Bohr's experiment, he subjected these things to lots and lots of light, and he found these light patterns. Okay, these spectral patterns are consistent and unique for every atom. So the spectral pattern for hydrogen is very different from helium, which is very different from lithium, which is very different from argon, and so on and so on and so on. But for each atom, it's the same. Hydrogen always has the same spectral pattern. Helium always has the same spectral pattern. And what's interesting is there are actually very, very few colors produced. So what he determined from this is that the electrons have to have specific energies. So instead of Bohr saying, hey, here's the nucleus and electrons can be wherever, Bohr said it has to be here or here, but not in between. Okay, you cannot have an electron that's there in between. Instead, it's got to be here or here. We now know those circles are called orbitals. And so you have Bohr's model of the atom. It says once again that you've got the positive nucleus in the center, but the electrons orbit the nucleus at specific distances, and these distances right here are called orbitals. And that when you absorb energy, so in other words, whenever this electron absorbs energy, it kicks it up to the next level. And whenever it loses energy, it emits light or something like that, it actually moves down from one orbital to the other. Okay, then we have the Chadwick experiment. And the Chadwick experiment is something that maybe you're not familiar with. What it actually did is they used a polonium source, which is a source of alpha particles, and they actually used these alpha particles and they fired them at beryllium. And whenever they fired them at beryllium, the beryllium actually lost mass, and so that mass that it lost was in the form of neutrons. Now, they didn't know it was a neutron at the time, but what happened is it would lose mass without really losing atoms, which is kind of interesting. So whenever these neutrons came off, they actually set it up to where they wanted to figure out what these things were. And so they set up something called paraffin wax that's right here. And the paraffin wax, these neutrons collided with the paraffin wax and actually turned into protons and electrons. So at that point, they became the idea that neutrons consist of a proton and an electron kind of combined. And so that gave the essence that it's a neutral particle because you have a positive and a negative that cancel each other out. Okay, so now we know the particle has a mass that's similar to a proton. We know that the particle is capable of being converted into a proton and that it resides in the nucleus. And this is Chadwick right here. Okay, you don't often hear the Chadwick experiment referred to. They just said, oh yeah, and there's neutrons. But neutrons were particularly difficult to detect because they didn't attract to the positive side or the negative side, and they're big. So neutrons were very, very, very hard to discover. Now we come to the model of the atom. So generally what we refer to as the last classical model of the atom is basically this. You have a nucleus which consists of protons and neutrons in the nucleus that are combined using something called the strong nuclear force. Okay, that's the reason why these two positive charges right here can be held together. Okay, so the nucleus is held together by the strong nuclear force. And you have electrons that surround the nucleus with distinct energies that are called orbitals. And they move very, very quickly in a circle because these electrons are attracted towards the positive nucleus because opposites attract. So that's generally what we refer to as the classical models of the atom. Then we have something interesting. There's something called the Davisson-Germer Experiment. And what they were doing is they were testing what was called de Bruglier's hypothesis. And de Bruglier's hypothesis was just basically this. De Broglie was a graduate student, and he was trying to get his PhD, and he came up with the idea, well, what if we treat electrons like they're waves, just like we treated photons like waves and particles? What if we treat electrons like waves? And he was expecting to see some sort of wave-like pattern. And what they did in the Davisson-Germer experiment is they actually fired electrons at a nickel crystal. And when you fire electrons at a crystal, okay, if you were to fire light at a crystal, you see these interesting patterns. Okay, they're called diffraction patterns. And you have this bright spot, and then you have a dark spot, and then you have a bright spot, and then a dark spot, and then a bright spot. And that's because of the wave-like nature of light. Well, it turns out when they did this with electrons at a nickel crystal, they actually figured out that these electrons can scatter as well. Now, what this actually meant was the fact that electrons can't really be treated as particles, but instead are treated as waves. So this is what you see. These are the interference patterns that you see. You see these lines that, hey, here's the electrons, and then in between is not electrons. So this is the interference pattern that says, okay, well, there's got to be something else going on here because the electrons aren't acting quite like particles. Instead, they're acting like waves. And so what they did is this actually took something from this Ernest Schrodinger, his name's hard to say, Schrodinger came up with this idea that, hey, what if we treat the entire atom like it's a wave? Real specifically the electrons, but and he came up with this equation. This is a modified version of what is called the standard wave equation in physics. Now, he took this idea of the wave equation and he applied it to the electrons and came up with this equation. You will not cover this equation right here until maybe your second or third year of chemistry/physics in college. Okay, so this is beyond the scope of this class, but you need to know the idea that he treated electrons like waves based on experimental evidence. So that's what we call a quantum model. And the difference between a quantum model and a classical model treats electrons like particles, and a quantum model treats electrons like waves and talks about the position of electrons in terms of probabilities. So you have the Schrodinger model of the atom, and one of the things for the Schrodinger model of the atom is you can't know the position of an electron. You can't say the electron is here and it's going around in a circle. You can't say that. Instead, you say there is a probability ring in which the electron is most likely within this ring right here, and I'm going to call this ring an orbital. That's what they're referring to when they talk about orbitals in the future. They're saying that 90% of the time an electron is existing in this particular part. Now, there's other parts of the time where the electron's right there, or it's outside of the orbital. But instead, the Schrodinger model refers to these orbitals as the 90% mark. So we look at example A1. It says the Bohr model is often referred to as the last of the classical models. Explain the difference between the Schrodinger model and all previous models, and we just did that. It is primarily in how you treat the electron. Is the electron treated as a particle, in which we talk about absolutes? In other words, we say the electron is here, it has a mass of this, it has an energy of this, and it is this far away from the nucleus. Those are the classical models. When we talk about the Schrodinger model or the quantum models, we say, here's the nucleus. The electron is probably over here somewhere. Okay? We don't know exactly where, but it's probably within some sort of ring right here. We don't know exactly where, but 90% of the time that it's right there. We don't know for sure where it is, but we're pretty sure that most of the time it's right there within this margin of error. That's the biggest difference between the models. How would the Bohr model differ? How would the Bohr atomic emission spectrum differ if the Rutherford model was valid? And the key is it isn't. So this is an interesting question because this is kind of an AP level question because it asks you to compare and contrast two models, and you're supposed to say, okay, now if something were different, how would it change? So if you look, the Bohr model of the atom says electrons are here or here, or if you had another one, here. In this case, in the Bohr model of the atom, an electron can go from here to here, or here to here, and produce light, or it can actually go from here to here as well. So there are three colors of light that can be produced. If you had the Rutherford model of the atom says, hey, there's the nucleus, and electrons can be wherever they want to be. So if we want to have an electron here, great. If you want to have an electron here, great. If you want to have an electron here, great. Well, that means that you can have light produced here, 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 here. In fact, you can have every single color of light produced. So if the Rutherford model of the atom were correct, this would show all colors. You would start with purple, and you would see all colors all the way to red. There would be no black spots in which there are no color. Whenever you have the emission spectrum for individual elements, you see much narrower bands like this. Now this is actually a mixture of elements, so don't think of this as evidence of the Rutherford model. This is actually a mixture of elements, which is why you have so many lines.